Welcome back to our series on probability theory. I'm Mark Ledbetter, and this is lecture video number 8, Independent Events, Part 1. This is section 1.4 in our textbook. So last time we talked about conditional probability, and we talked about a multiplication rule. And we talked about extending this to any k finite number of events. So in this section, we're going to define independence of two events. We're going to talk about pairwise independence and then mutual independence. So let's get started. So our definition, events A and B are independent if and only if the probability of A and B equals the probability of A times the probability of B. So if they are dependent, then it would be probability of A times the probability of B given A. So this is dependent. Okay? So what we're saying here is if they're independent, then the probability of B given A is equal to just the probability of B, and that's very important. So some terms, independent events, that means the same thing as statistically independent, stochastically independent, or independent in a probabilistic sense. So we're using this symbol that looks like a right angle symbol for independence. So my first example, let's talk about flipping a fair coin twice. And we're going to use a tree diagram to get our sample space. It's easy to do, and it keeps us from making a mistake or missing one. So heads on the first, tails on the first, and then the second flip is down here. And then we have our sample space. So let's define some events. A is that we get heads on the first flip, tails. B is tails on the second flip, and C is tails on both flips. So I'm going to write out what each of these events, the results or outcomes in each of the events. So A has heads, tails, heads, heads. B has heads, tails, then tail, heads. And C is tails, tails. All right. So there are four possible, so N of S is equal to 4, and there are two outcomes here in each of these, A and B, and one outcome in C. So the probability of A and B is 2/4, and the probability of C is 1/4. We want to find the probability of B given C. So we're going to look at the probability of B and C divided by the probability of C. So we look at B and C, and they have in common this. So there is an overlap, and in fact, the overlap is the whole, the intersection is the whole event C. So this is going to be the probability of C divided by the probability of C, which is equal to 1. All right. And so notice that C is contained in B. Now, let's look at, let's find the probability of B given A. So again, this is going to be the probability of A and B divided by the probability of A. We look at A and B, and in common, they have heads and tails. So this is the probability of the set heads, then tails, divided by the probability of A. And we said the probability of A is 2/4, and the probability of heads and then tails is 1/4. And so the fourths cancel because they're both the same denominator, and we end up with 1/2. All right. So here, this is also equal to the probability of B, which is 1/2 or 2/4. So this says that the probability of B given A is equal to the probability of B. Therefore, A and B are independent. Notice here, this is not equal to the probability of B in part A. So the probability of B given C is not equal to the probability of B. So B is not independent of C. Now let's look at another example. Here we have a red die and a white die are rolled. This time we're using regular die. They have 6 sides. So I've written out the sample space over here, red along this side and white along that side. And instead of writing all of the notation, 1-1 should be written this way. But I'm using shorthand. You're welcome to use the same shorthand when writing out a table like this. All right. Now we're defining event A as a 4 on the red die, and event B as the sum of the dice is odd. All right. So with this, we need to find the 4 on the red die is here. Okay, so that's event A. Now, for event B, I'm going to change color, and we want an odd sum. So we have odd here. We have odd, let's see, here. And then 6, and then we have odd here. And then we have odd, let's see, so we've got this 9, oops. And then odd here. All right, so we've got 2, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So B has, N of B is 18. N of A is 6. All right. And we want to determine if A and B are independent. So here we have the probability of A and B is the way to do this. And we want to know, is this equal to the probability of A times the probability of B? Now, we can use a different color, say green, and we'll see that here is an intersection, here is an intersection, and here is an intersection. So the probability of A and B is 3 over 36. The probability of A has 6, so this is 6 over 36. And the probability of B, again, is 18 over 36. Now, I can do some canceling here, and I get a 1 and a 2. And then I can divide this into there and get a 3 and a 1. And in fact, this is 3 over 36, so A and B are independent. Very good. Now, let's define C as a 5 on the red die, and D, the sum of the dice, is 11. I'm going to use my eraser here and clean this up so we can reuse this. And now I want C is going to be a 5 on the red die. There's these 6. And then D is the sum of the dice is 11, and that's these 2 here. And then our intersection is going to be this value right here. Okay, so the probability of C is equal to 6 over 36. The probability of D is equal to 2 over 36. And the probability of C and D is equal to 1 over 36. So let's see if this works. We have the probability of C and D is equal to the probability of C times the probability of D, and it's a question mark. And so we have 1 over 36 equals 6 over 36 times 2 over 36. And here we have, on the top we have 12. This is 12 over 36 squared times 36. And so this will be 1, and this will be 3. And so this would be 1 over 108. And so this is not equal to 1 over 36, which is probability of C and D. So C is not independent of D. All right. So I hope that this has helped you understand the concept of independence between two events. Please don't forget to scan your lecture notes in by midnight tonight. Again, make them neat for you. It helps me to read them, but it's really for you. These are for you. If you have questions, please come to my virtual office hours. If those don't work for you, email me. I'm happy to try to set up a time outside of that. And I hope to see you next time in Probability Theory.